ATA provides mission analysis and design services to the aerospace industry. We have completed numerous mission analyses either independently or as part of a larger project. ATA's experience includes analyzing missions for launch vehicles, in-orbit operations such as rendezvous and lunar and Mars mission analysis. With our own set of thoroughly tested in-house tools, ATA does not rely on generic third-party analysis software. This is how we can provide flexible, yet highly cost-effective, high-fidelity mission design and analysis services. Space missions are complex and expensive. The designing of space missions is an iterative process where you must first define the mission objectives, characterize the mission and its concepts, evaluate the mission concepts, and fully define mission requirements. The last step in designing a mission is to allocate requirements to elements of the mission. Designing a space mission requires many different disciplines. At Advanced Technology Associates, we have the disciplines required to design space missions. In order to design an effective mission, there are many considerations a mission analyst must address, each requiring its own specific expertise. Here are some analyses ATA often performs when designing missions. The following example discusses how some of these elements were applied to a particular lunar mission. A customer of ATA asked for help designing a mission for two classes of payloads to the lunar South Pole. It was relatively easy to design a mission for the larger payload because of the available launch vehicles such as the Atlas and Delta. However, the only option for the small vehicle was the Minotaur. Since the Minotaur launch vehicle's available configuration had insufficient lift to satisfy the requirements, we designed a mission for the small payload using the Minotaur while augmenting it with various upper stages. Conducting trade studies as we proceeded, we performed trades on the spacecraft subsystems and built an equipment list from those traits. After adding customer-supplied payload mass, we determined the total mass required for the mission. This is an illustration of the mission trajectory. We conducted limited trades on the communications that would be required for this mission and the thermal requirements inherent in this type of transfer. We incorporated the results of these trades to design a mission that used an optimum 5-day transfer time from Earth low orbit to the Moon. We analyzed the avionics systems using an error budget from a separate analysis. This provided us a sizing of the propellant requirements for mid-course corrections. This analysis resulted in the selection of 3 different points along the trajectory where we could make optimal use of the solid propellant on board. We had to use a spacecraft rotational barbecue mode to control the thermal environment of the vehicle during the 5-day transfer to the Moon. The mission plan stops the rotation briefly at the 3 mid-course correction points, thereby providing a window of communication for updates and corrections. The avionics for this class of mission requires a low drift rate IMU. Nonetheless, a stellar star tracker was needed to update the spacecraft's attitude. Ground tracking was used to provide the data to update the vehicle's state vector. The final update of the vehicle's attitude and state vector was scheduled as the vehicle approached the Moon's south pole. The avionics system selected met the requirements that the vehicle touch down within a 5-meter radius of the landing site. Mission analyses like these can take extended periods of time, but we leveraged our experience to prioritize the analyses that we knew would be key to mission success. Here we see an animation of the deorbit and landing phases of the mission. The animation shows the lander approaching the lunar south pole. The Star 27 motor is used to provide a braking burn for the vehicle and to put the vehicle on a trajectory to intersect the landing site on the rim of Shackleton Crater. When the vehicle's horizontal velocity reaches 0, the Star 27 separates and thrusters on the motor accelerated quickly away from the lander. The gas generator on the lander is immediately ignited and the lander reorients to perform a correction burn. The lander adjusts for any ground range error due to variations in the Star 27 performance. In this idealized example, the error is minimal, so the propellant in this pulse is used mostly for attitude control and not for braking. The lander drops toward the Moon's surface. The warm gas system holds the vehicle's attitude and controls descent with minimal thrust while the vehicle gains vertical velocity. As the vehicle attitude approaches 50 feet, a second pulse provides a strong burst of impulse to slow the vehicle and zero out vertical velocity. The vehicle then descends to 10 feet, where it hovers while the remaining propellant gas is exhausted. The lander finally drops to the surface. This study resulted in a tool that a customer can use to analyze missions to the Moon. The tool was designed to be reconfigurable so that it can be used for either small spacecraft or larger ones. We also built a trajectory analysis tool that did a calculus of variations analysis of trajectories to the Moon. This work resulted in a technical presentation delivered to both the client and NASA. At the heart of what ATA does is the development of software tools for the aerospace industry. We achieve our mission design goals in a cost-effective manner because of a rich heritage of refining our in-house software tools. By contracting with ATA, customers benefit from our experience and cost savings methods. For more information about mission analysis projects or capabilities, please select Contact ATA on the main menu of this CD.